Stay focused. Alrighty, we're going to rock and roll on some compactness in just a minute. Let's take a few minutes first. We need to do this on Monday, so just settling in to check on yourself. For the next couple of minutes, can you do nothing? Can you just completely veg? No effort. Effort starts coming your way by thought. You just knock it to the side like a ninja. Find your mind grabbing something. Relax. Let it go. Before we get done with this, just in your mind, give yourself some good wishes. Talk to yourself like a good friend. You deserve love. You deserve to be happy. Let's just come back, do some math. Man, I can't see anything. Barely see with the glasses. All right, my friends, compact sets. Oh, what happened, Kayla? What's
There you
going
go.
on?
It was just blurry.
Oh, thank you.
No, it's not blurry.
Thank you. You are the production. What is the person in charge of? The producer.
Producer.
You're the producer of this show.
This is excellent news.
Appreciate your volunteer work.
Can I put that on my resume?
Yeah, absolutely. Absolutely. All right, I gotta just grab out my book here. So last time we had a lively, if slightly coerced, discussion over compactness. So let's refresh everyone's mind on this, and perhaps you're hearing this for the first time because you didn't watch the recording, which I did put up, right? Did I get the recording up?
I didn't get the email.
Oh shit. Oh man. Damn. Oh no, I was editing it and then it takes forever and I never uploaded. I'm sorry. Okay. Fuck it. Let's review. So we're talking about this essential property called compactness. We say a set is compact. We use K probably because I bet the German word for compact, or maybe the Russian word is compact. A set K is compact. And we talked about a couple of definitions. The definition given by our book, this is going to be a list of equivalence things, and one nobody's seen yet. So So the first one is if it is, make sure this is a subset of R, because otherwise this isn't true. Every sequence in K has a convergent subsequence. That's the main characterization of compactness given to us by the author Abbott. And it's a great one because this applies everywhere. This is the definition of compactness that's going to work in R, in Rn, in n-dimensional space, in infinite dimensional space, in every other place in mathematics. The next characterization is equivalent to this only in real space, finite dimensional real space. I mean, for us, our dimension's 1, but 2, or 2, K is closed and bounded. That's the main characterization you want to use in this class. So I tell you a set is compact, you immediately translate. You have both these properties, closedness and boundedness. If you know a set is closed and bounded, then it is also compact as per definition 1 right here. Here's a quick idea of why that's even equivalent, just the quick proof. If I have a closed and bounded set, and I take a sequence in K, any sequence, I don't know anything about it, because K is bounded, so is that sequence. So K, this is like a quick proof, K bounded implies this sequence is bounded. Bolzano-Weierstrass tells us that bounded sequences have convergent subsequences. So Bolzano-Weierstrass implies there exists an X of n j converging to some X. Converging to some X. We don't know that X is in K until we take in now closedness. So I have a sequence in the set, it is converging. In other words, X is a limit point of K, and closed sets contain their limit points. So since X is a limit point of K, and K is closed, X is an element of K. And this should say, actually I need to fix this up just a little bit, has a convergent subsequence converging in K. That's the essential part, because I forgot to put that up here, converging in K. So that limit is actually in K. Sorry about that. I think I missed that last time too. Yeah. But that's a quick little proof. So, let's warm up with a couple examples. Let's look at some sets. And we did a little of this last time. Let's pick it up. So, just some quick refreshers here. We looked at exercise 332, and we had the various sets. And the question was, are these compact? And let's go through them again really quickly, since you didn't have the benefit of seeing this. And then we're going to keep going on here. And these will maybe help on the homework that I should have probably asked if there was questions on. So let me get there again really quickly. And I'll see if there are questions after we do this example. Ooh, and then one more. Okay, we'll see how this goes. Cool. So, going through, thinking, compact is the question, i.e. closed and bounded. Has to be both. Closed and bounded? Michael, you say no, sir. Why is that?
Because it's not bounded. Whatever you think is the biggest, you can only find one bigger.
Perfect. Not bounded. That blows it. It has to be both things. So this is not compact, and I abbreviate that CPT. Again, taking more time to explain the definition, the abbreviation, than it saves, but I do it anyway. Now really elaborating and belaboring the point, using up all the savings that I'll ever have in my lifetime for abbreviating that. So not compact because not bounded. Compact. Question mark. I'm not staying in. Is it bounded? Definitely bounded, right? It lives in 0 to 1. So this is bounded. By the way, this top one was closed. We could have put that up here. So this one is bounded. Why is it not closed?
Because it doesn't contain 0.
In fact, it does contain 0, because 0 is irrational. So that would be in there. There are things it doesn't contain, a lot of them. What are those things? Irrationals, right? So this doesn't contain any of the irrationals in the interval 0 to 1. That doesn't mean it's not closed. Why is it not closed? So square root of 2 over 2, bless you, is in this interval. It is not rational. What's the troubles? Why is that set not closed? Is this a limit point of the rationals?
It's not containing rationals.
So this is an irrational, right? Can I get a sequence of rationals converging to this number? Yeah, because I can do that for any number. There's always a sequence of rationals. So the square root of 2 over 2 is half of root 2, it's 0.707-ish. So we can get a sequence, so this is not closed, because square root of 2 over 2 is a limit point. There's there's infinitely many in there. Pick any irrational in there, you can find a sequence in there of rationals converging to it. Is a limit point. So we say here, for example, x1 equals 0.7, x2 equals 0.70, x3 equals 0.707. Just take the decimal expansion bit by bit. And that limit point is not in the set because it's irrational, so this can't be closed. But not in. Lord, that's a cue. This is where we ended up last time. Cantor set. Cantor set was defined. You get to see all this again. Hopefully it's actually like, oh, that's nice. I feel like I'm on top of this stuff. So a Cantor set starts out like this. Remove the middle third at each stage of the existing, right? These are all closed sets. And the Cantor set is defined to be the intersection of all those. Equals 0 to infinity. Is the Cantor set bounded? Definitely bounded, right? It lives in 0 to 1. So bounded. Is it closed? That's interesting, Michael. Why you say that?
Because each one of them can be expressed as an infinite binary thing. And that feels like with what we were doing with over there, where we can get close to whatever we want, but there'll be some things we can't hit.
I love the way you're thinking about this, but that sounds more like a cardinality argument maybe That's definitely a good cardinality argument. But it turns out it is closed. And let's see why. Do you agree that each of the stages is closed? It's just a finite union. At any stage, it's a finite union of closed intervals. And if I look at result, we didn't talk about it, but it is in the reading. Theorem 3214 says that a union of a finite collection of closed sets is closed. Each of these is a finite union of closed sets, therefore they are closed. And then the intersection of an arbitrary collection of closed sets is closed. So if I take a bunch of closed sets, no matter how, let's see, a gamma here, and gamma is from some index set, each one of those is closed, this is closed. If each C sub gamma is closed. That's not a gamma. I don't know what is that? That is a gamma, right?
Yeah.
But then that was a lambda or something, right? There we go. Okay, sorry. Yeah, that's better. To keep those things consistent, it doesn't really matter. But here I have an intersection of closed sets. It's an arbitrary it's an infinite intersection. It doesn't matter. This is closed by theorem, and we didn't cite this last time. 3214, part 2, and 1, really. Both parts are needed to kind of argue that total closedness. The Cantor set is a compact set. Cool. Now we're in the new territory. This is a challenging one. What does it remind you of? Just like in your math history, what kind of ancient sounds do you hear in the basement? Some rattlings in the attic.
It's my favorite.
What?
It's my favorite.
Yay! It is?
No.
No, okay, no.
Well, I mean, it's not my favorite.
Which math does it remind you of? Series. Calc 2?
Yeah. P series.
Maybe this class, because we talked about them a little bit. So, what do I know about that?
It's convergent.
It is convergent, right? Convergent P series. So this converges. Now you may not know what it converges to, but you will in just a minute. You can prove, and you have to go to a thing called Fourier series, and maybe Trinity knows something about Fourier series, yeah. You have to go to Fourier series to show that this actually converges to pi squared over 6. So, this set is actually a sequence of partial sums. It's just the nth partial sum here. Okay, plug in k squared. I know that this sequence converges to pi squared over 2. Pi squared over 6. Is pi squared over 6 in this collection? So pi squared over 6 is a limit point. Is it in here? Is pi squared over 6 irrational? Just probably, right? Probably. We don't 100% know, but yeah, it probably is. So every step along the way, each one of these things is actually a rational number because it's just a sum of finite number of fractions. So everything in this set is rational. The limit point is irrational. So this is not closed because pi squared over 6 isn't any element of this set. Is it bounded? Is that set bounded? Yes. It's a convergent sum, right? So if it wasn't bounded, it couldn't converge. So if this sequence of points was not bounded, there is no sum here. This thing is definitely bounded. In fact, it's actually an increasing sequence of points, right? So the first one's going to be 1, and then the next one's going to be 1 plus a fourth, so 5/4. And then the next one's going to be, I'm not going to add 5/4 and a ninth, I don't care what that is, but it's this one here, 5/4 plus a ninth, and then on up, and we know that pi squared over 6 is an upper bound on that. It smashes up against that. This is the supremum of the set. What about this one? So this isn't compact, right? Bounded but not closed. Is that a compact set? Start erasing. Well, I need erasers. Go. Is it bounded? Sure is, right? What's it bounded by, Michael?
1.
Perfect, right? Smash it, it's approaching 1. You can see that all those numbers are going to be less than 1. So this is bounded. Is it closed? Cool. Because why? Because it contains 1. Yes, beautiful. So if we had left this out, it would not be closed. But we can see that 1 is a limit point here. So 1 is a limit point, and 1 is in the set. So we're good to go. Yay, thanks for tossing that 1 in here. That is a compact set. Cool. Does that all sound right and true? Yeah. So now let me back up to where I should have been to start class. Does anybody have anything they want to talk about on that last homework set before we go on? Because I got a crazy story to tell you, but it's going to make everything, you're not going to want to talk about that after this. No questions? Do we need more time on the homework? Yes. Okay, I see the slightest nods, yeah? Okay, we're good. Okay, get it to me on Monday, okay? Sound good? Awesome, it's great. I don't give a shit. I haven't even graded the last stuff yet, so it's like, I've got my own work to do. All right, so here's the idea of compactness, this idea that every sequence in the set contains a convergent subsequence in the set is a great way to think about compactness in general. But I want to show you something that's not compact, that's really interesting. My favorite not compact set. So my favorite, and it could be your favorite too, that's okay, not compact set. We have to go way out into space for this. Let's just kind of work our way up there first. So if I showed you this set, just let's work our way up. Like I said, if I said I've got the set of all x1, x2, x3 such that x1 squared plus x2 squared plus x3 squared equals 1. In 3-dimensional space, what is that? Yeah. Michael's owning it. He's created one in space. It's a sphere. Radius 1. So this is a sphere in R3 of radius 1. And I could continue this, right? This idea that here's an n-dimensional sphere, so it's the collection of n tuples. So that's an n tuple. And we want the sum of x sub k squared to equal 1. So this is an n-dimensional unit sphere. All these things are compact. These are compact sets, and we can prove that with a lot of work that we're not going to do. But if you just imagine you've got a sphere, and let's just look at the three-dimensional sphere here. So I've got the three-dimensional sphere. If I start putting infinitely many points on it, so here's a sequence. Since I'm putting it on the sphere, it's bounded. It's already bounded if it's on the surface of the sphere. But if I build that infinite sequence, I can play the same game where I say, okay, now cut the sphere in half. In one half, there's infinitely many points. Grab that half. Cut that half in half. Look for the infinite section. You remember this game where I kept cutting the infinite half in half? And in the process of that, I whittled my way down to a limit point. So that game, sorry, that's not like well described or anything. Like that's not noteworthy. It was all in my words. But it's that game of just cutting things in half until you get a limit point. That all goes to hell the minute we actually, which is a pretty big minute, we shoot up into infinite dimensions. So notice this is finite dimensions. This sum stops. But if I look at the sum, the collection of all points, x1, x2, x3, notice that's actually just an infinite sequence now. But we can think of it as a point in infinite dimensional space. Point in R infinity, such that the sum of all those points squared, their magnitude squared, equals 1. That is the infinite dimensional unit sphere. So this is infinite dimensional unit sphere. And this was one of the things I mentioned this on Monday. I don't know if I mentioned this any other time in our class, but this was one of the things I would think about when I was having trouble falling asleep in grad school. I would think about this infinite dimensional unit sphere and the fact that it wasn't compact. And there's a cool way to see this. So we're going to build a sequence on the infinite dimensional unit sphere. And that sequence is the simplest sequence we could possibly think of. It's just going to be the cardinal points on the sphere. So what I mean is, consider the sequence on, on this sphere. And picturing the sphere is the part that put me to sleep. Trying to picture it anyway. But we've got a list of points, so we're going to take one. Yeah. And then so in some ways, if I was in the 3D sphere, what I'm actually doing is this. I'm picking the points on the positive x-axis and the positive y-axis and the positive z-axis. So I'm just picking those points on the sphere. But I can do that forever on the infinite dimensional sphere. And so I ask myself, okay, I've got an infinite sequence here. So here's an infinite sequence. It is bounded as well. It lives on the sphere. The magnitude of all of those is 1. All of these are just unit magnitude, bounded, because each point has length 1. But it never accumulates. It doesn't lump up like this picture I was showing before. It doesn't lump up like things do in finite dimensional space. Because the distance between any two of these points is the square root of 2. So let's just think about it. Can you see that kind of, that's going to work? I mean, what is the distance between any of these two? right? It's Pythagorean theorem, right? This squared plus this squared is this squared. So the distance here is root 2. The distance between any two of these points is square root of 2. Just take the difference. Do it like you normally would. Distance between, so I put a but here, any two of these points is the square root of 2. They never accumulate. So the unit sphere in infinite dimensions is not compact. And that's like a really good example. You gotta go to infinite dimensions to get something weird like this. So thus, there is no convergent subsequence. Hence, it is not compact. And so yeah, I would just lay there in my brain, picturing these points, and just, I don't know why this was so soothing, right? There's something about it. Just simply trying to picture this thing, even a little smattering of it is I think, good for you. And you know math is good for you if it hurts, right? It does. Like, you're not getting anything out of it if it doesn't hurt. It's fun and soothing, but it's not growing you as a mathematician. So anyway, that's one of my favorite stories. Thanks for listening. Let's talk about another characterization of compactness that is mildly disturbing, very different from anything you've ever heard before. We have to get some definitions out here before we can even do it. You know it's going to be good if we've got to define things before we even talk about it, right? So here it comes. Let A be a subset of the reals. An open cover of A is a collection of open sets and we don't know how many. I'm going to call it O sub, let's use lambda. Lambda. Use your favorite index, I don't care. It could be infinite, it could be finite. We don't know anything about it beyond it's a collection of open sets. But we have this collection whose union covers A. So it's just a collection of open sets that when I look at them in totality, A lives in the mist produced by these open sets. Example. Let's say the set A is closed interval 0 to 1. I don't have to try too hard here. Literally, here's an open cover. Anything, let's see, so here's your set. Just pick some sets that cover it that are open. So let's see, let's go from negative half up to 3/4. And then pick another one. You don't want to leave any space, so let's go from positive a half to 3/2. So that'll be 1/2 up to 3/2. That is an open cover of the set A. Make sure this is all registered, please. And let me know if we need to talk about it.
So it must be the union of those two insets.
Yes, ma'am. Yeah. So this is an open cover, and note that A is contained in the union of those two things. So yeah, thanks for saying that, Kayla, so I can make this a little clearer. But there's infinitely many ways this could happen, right? That's just a very simple example. Lots of ways that I could cover that thing with open sets. I mean, here's another one. Here, just R. there's an open cover. Covers everything. Done. Really simple. So come up with your favorite open cover if you would like a different example. Come up with a new favorite open cover because you probably never covered anything with open sets before. So an open cover of A is this. A finite subcover is any finite subcollection from an open cover of a set A that still covers A. Really strange ideas today. Lots of strange ones. Infinite spheres. All this weird stuff. So let's actually try to come up with a nice example that's actually more interesting than those. So how about this? Let's see here. The collection n, comma n plus 1, and let's see, n equals 1 to infinity. Let's do, excuse me, n plus, yeah, I think, let's see. Well, I want this to cover everything for the most part to the right. So let's see here. Let's see, that would be 1 to 2. And 2. Oh, we got to do this n plus 2, excuse me. We got to skip so that they overlap. This is an open cover of the set 2 to 3. And I'm just picking that as a weird thing. So look at what this open cover does. It goes from 1 to 3. So that's one of the sets. And then the next one goes from 2 to 4. So it's hard to draw them, right? But 2 to 4, and then the next one's going to go 3 to 5. So you've got these sets kind of like this. And I'm drawing these offset so that you can see them, actually. But it's basically a cover from everything to the right of 1 on up to infinity. But it certainly covers that set too. And make sure that you believe that. That the closed interval 2 to 3, which is in here, there's 2 to 3, that is covered by that open cover. If you take the union of all of these, and let's actually see that, you could say the union of n to n plus 2, n equals 1 to infinity, is going to equal the open interval 1 to infinity. So certainly, this is in there. What's a finite subcover I can pull out of here? We'll make a list of it. Can I start with, let's see, what's the second set? So I could grab 2 to 4. There's actually not an infinite number of right answers here. 2 to 4 and 3 to 5. Do you see that that covers the set still? Yeah? Trinity, is that making sense? Maybe, yeah. I'm sorry, say that again.
Wouldn't it leave out 2 if we're looking at 2?
Oh, it's okay if 2's out because I'm, oh wait, you're right. No, it's not okay.
It would be the 1
You
plus
busted
3,
me.
2.
You're solid, thank you. Thank you so much. Yes, I actually should have gone to the left, shouldn't I? So I actually wanted 1 to 3, then 2 to 4, and that does it. Thank you. could see something wasn't right there. Thank you. That covers. That does it. The other one didn't. There's other finite subcovers. You could just toss in, and now that you've got it covered, toss in whatever other sets from here you want, and that's also a finite subcover. As long as you only add in finitely many things. All right. Then we're going to practice with this. So if that idea is still seeming a little nebulous, hopefully it'll become clear as we work through this. But let's go back to that definition. K and R is compact if one of the following holds. And we've already got two things. We know that every sequence K has a subsequence that converges in K. And I'm just saying the same thing again, but it never hurts to build these things, grind them into your brain. Converges in K. 2, K is closed and bounded. That's equivalent. And then lastly, this is the most interesting characterization of compactness. Every open cover of K has a finite subcover. And you could say here has, sometimes the word admits or allows. Those all work quite well there. And we'll just say of K so that we're clear on what's getting covered and sub-covered. All right, let's play. It's because this is a very strange characterization. And let's look at some places where it fails. So, example time. Consider 0 to 1. Is that compact? Open interval 0 to 1. No, because literally I just said
It's
open. Right. It's got to be closed. It needs to be closed and bounded. So we know this is not compact. But let's demonstrate that using the open cover thing. So all I have to do to blow this is if I can produce one open cover that doesn't have a finite subcover produced from it, that means the set isn't compact. So we need to produce a single open cover that allows for no finite subcover. Can you take a minute, please? This is going to fall back on an idea that I always say, this falls back on this idea, and it's a primal one in this class. Can you cover that set? Okay, you still think that's cool? No rush. No rush. You could, but then there would be a finite subcover. So you could just cover it with itself since it's open.
How could you make a finite subcover?
Because there's only one thing in that cover. So it by default is a finite subcover. So what you need to do is look for an infinite subcover.
Okay.
That's good thinking though. Yeah. You think you got something, Michael?
I was just gonna do infinite series that converges to one.
Yeah, you got to do it. Got something over here that I got ideas. Got a nice hyperboloid or something over there. You got any ideas here? Michael, I don't want to take away any thunder because I think you're brewing some up.
I did the sum from 0 to, I guess it doesn't mean so. I did 0, comma, and then 1 over 2 to the n for all of them, for n0 to infinity.
So like this,
Yeah,
and then n runs from 0 to infinity. Is that what you said?
yeah.
Cool. So, damn close, but alas, there is a finite subcover from this. So Michael's set, this is the right thinking, 100%. Notice that Michael's sets they actually contain 0 to 1, and that's the problem. Because I could just cover this with like, oh, there we go. Just grab that 1 and it still covers the set. So let's get rid of that.
So,
What were you gonna say, Kayla?
so
We can try this.
yeah, and from
Oop, sorry.
yeah.
Like that. And then what do we got now? So now we've got 0 to half, right? But we're still missing, now we're missing, alas, this stuff over here. You're really thinking the right way though, for sure. What if we make this end, this right end, move to the right? And so I think this is kind of what you're trying to get going there. But if we did this, and we can use your set, let's look at this. And I could even just we could make life a little easier, right? Just do that, less weird stuff going on. And so then n equals 2, 3, let's have all these, I don't want to put 1 here, so I've got something that's not actually an interval. So what is this gonna do? It's 0 to a half, 0 to 2/3, 0 to 3/4. Yeah. And if I took the union of all those, it covers this set. So notice that this thing right here is an open cover of 0 to 1. Make sure you see that. Make sure that that works for you. But I can't take any finite collection from there and expect it to cover, because it will eventually have a rightmost element, and it's going to leave a big old gap on the right-hand side. So let's make this kind of formal. But no finite subcover exists. Let's see, what is a finite subcover going to look like? It's basically going to be like 0, 1 minus 1 over n1, 0, 1 minus 1 over n2, and then on up to 0, 1 minus 1 over n sub n. finite subcover's gotta look like this, bless you. But that means it's not gonna cover anything past the max of 1 minus 1 over n sub j, where j equals 1 to L, right? So if I take the rightmost endpoint, that's all I'm trying to say here. If I look at the rightmost endpoint from this finite subcollection, it's gonna bomb out somewhere right here, and it's gonna leave us woefully short of 1. And it might not even be woefully short. I mean, this could be 1 minus 1 over, a Google that I like to say here. But there's still, might as well be infinite amount of space between here and 1. So here I'd say, can never cover the rightmost part. Please make sure that makes sense, because I'm happy to keep talking about it. It's a strange idea. Let it register. And that's only because that set is not compact. It's not closed and bounded. If that set is closed and bounded, like this, we can't do that. And let's talk about why that would be the case. So let's just say I toss in these endpoints and make the thing, now it's closed and bounded, right? And I can't really play the same game again. I could use this as part of my cover, right? So I could take this cover, and we go from 0 to 1, and I'm gonna use this, and it's got all its weird stuff. It's got these right endpoints, and they're cruising this way and eventually covering the whole thing. But I still have to cover 0 and 1. And the minute I do that, look what happens. The minute I cover 0 with an open set, and I cover 1 with an open set, that takes care of that space that was never filled here. It's gonna spill in on this side. And so eventually, if you covered up this far, you'll be able to get a finite subcover. You just include that, you probably include that, and then just some little finite list inside here will cover it. So tossing in those endpoints changes everything. Very strange notion. Man, I hate watching recordings of myself teach. I was checking out, when I was trying to edit that recording from Monday, I started watching it and I was like, I said something so goddamn many times. It was like, all right. And I was like, I just wanted to slap myself. Just like, this shut up. I'm sure all the stuff, like if you were gonna imitate me, I don't even want to know what that would be. It sounds terrifying. So this theorem that we had before, the equivalence of closed and bounded, compactness, and this open cover finite subcover stuff, that's all part of what's called the Heinie-Burrell theorem. So Heinie-Burrell is all of the, basically gives us the characterizations of compactness. And I thought about going through the proof today, but it just feels wrong right now. I don't know. It just doesn't feel like it's something we should do at this moment. And instead, we should do something else, like work on a problem together. Indeed. Check out problem 334 on page 100. If nothing else, to see if your mind is like a 12-year-old's, just like mine is when you look at that problem. Because that brings out the worst in me, just the letters and symbols that they put in that. I'm like, really? Did you know what you're spelling here? Kind of. Okay, so anyway, yeah. A brief moment of levity and rears its head in real analysis. Okay, let's take a look at that problem though, nonetheless. Problem 334. Just to explore some of this stuff. So we have K is compact, F is closed. Decide if the following is compact, definitely closed, both compact and closed, or neither. Okay, so the first one is K intersect F. What can we say about that set? I just want to practice these definitions really more than anything. Suspicions. What's that? So, did you say bow?
Yeah. Maybe? If that's right. No, I'm just kidding. Yeah, that's my conjecture.
Bit. What is your conjecture? Bow.
Bow.
Bit. So, talk with me, Kayla. What were you thinking? So, how do we know if something's compact? What's the best, easiest way?
It's closed and bounded.
Solid.
So then we know that the union between two closed sets must be closed.
Or intersections as well? Absolutely.
I said union, that's my intersections.
That's all right. But we do know that. We know both those things. And you're just like educating us on the fact, the full spectrum of things that are possible.
So I feel like it's definitely closed.
It's definitely closed, right?
Whoop, whoop.
Solid, yeah, beautiful. Check it out. So K is compact, therefore K is closed, and it is bounded. So this must be closed because both are closed. Why is it bounded? Michael.
If F is closed, it converges to something we know that every converging sequence is bounded.
Ooh, you're getting too fancy. Too fancy. We know K is bounded, right? What happens when I intersect something with something else? Does it get bigger or smaller? Smaller. So this is a subset of K, actually, right? So this, K intersect F, and all that stuff you said was true. It's just like, yeah, it's too fancy. Subset of K is bounded. That implies K intersect F is bounded. And we got closed and bounded, so K intersect F is compact. These are good exercises for us to be doing, I see. This is good. Oh, good Lord. I'm just gonna put it on the board. This one is tricky, so we're gonna have to really piece through it, but. Okay, so the next one. I know, they had to know. They had to know. Come on, dude. So what is this bar on top means the closure of. So this means add in all the limit points. So this up here means closure, i.e. union in all limit points. So that right off the bat tells us this thing is closed. It was literally built to be closed. We did this stuff. We fucked it up, and then we closed it. So we know it's closed. Now the question is it bounded? Closed by construction. Is it bounded? I don't know the answer. I'll have to think along with you. Yes?
Use this one.
Let's see. Yes, definitely that. So Michael is pointing to Theorem 3.213, characterization of closed sets and their complements. We talked about this, I think, on Monday, but if I have a closed set, I shouldn't use that. Its complement is open, and vice versa. I'm going to show up, I'm going to find out where Abbott is giving a talk and just sit in the audience to wait to ask him about that problem.
So if you pull out your textbook on real analysis, can you explain to me?
Exactly how much had you drank when you wrote this part? Those old analysts, boy, those Russian and German analysts, they would be hammering it all late into the night. There's stories of, I think it was Weierstrass and Hardy drinking vodka late into the night, working on analysis. It sounds exhausting and horrible. To me, that didn't sound at all pleasant. What do we think? And all we have to do is come up with a counter, an example of an F and a K, so that this thing is not bounded. Think you got one? Maybe?
Maybe. We know that K is also closed.
Yeah.
So
Yeah.
the theorem applies to K as well.
Exactly.
Which means that we're taking the union of two open sets,
Indeed.
which must be open.
That's true. Yeah.
So therefore it would, ooh.
And then we close it, so we're definitely closed too. So we're thinking bounded though. Think in terms of boundedness. Can I produce a closed F and a compact K so that this construction here is unbounded when we do it? I'm going to try to be pretty unimaginative. There's no prohibition on them being the same set. They're both closed. They're in fact both compact. What is F complement? What is K complement? Michael, sir, yeah.
It's the union of the open sets negative infinity to 0 and 1 to infinity.
Solid, yeah, that's the same for both of them, yep. Yeah, it's everything else. except those two little nice chunks. Then the union of these two, see, it was nice to pick F and K to be the same because now things become a little simpler. So the union of those two, totally gonna leave this up for calculus to see, is the same. Yeah? What is the closure of that? Oh my God, I just came up with a shirt idea for the math department. It says something like math or so. There's some math thing, and then it has that. Regis math, fuck yeah. No, it
Can we
doesn't say
please?
fuck. No, it's the closure of the union of a compact set. Close it. What is the closure?
You just union in the closed interval.
Yes, yes. I said, Pip. Yeah, just toss in the endpoints on the soft parts, right, and then close it off. Is that bounded? We say no. Just say no. No, that is not bounded, because we got a whole other problem if that was bounded to you. So this is not bounded. So this set is not necessarily compact. Is it closed though? Yes. Not bounded, but compact. Let's put not necessarily bounded, but definitely closed. So that means we can't count on it being a compact thing at all. So let's do one last one, since we have 5 minutes left. And I didn't get to see a good portion of you on Monday. So, that one was, shit. Okay, we'll just put it up. How about this one? That is set subtraction. That's probably a good one. Yeah, yeah. Compact, question mark.
If you make that shirt, I
What's
will
that?
buy it.
Say that again?
If you make that shirt, I will buy it.
Really?
Yeah.
Okay, all right,
Absolutely.
all right then. And then we'll just all wear them. Yeah, I know.
My boyfriend actually owns a printing shop, so I was gonna make it for you.
Oh, really? Oh, that's all. I do, I sell t-shirts, so I like have somebody else print them for me, but man, having them hand printed would be pretty sweet, so.
Size are you?
A medium, like whatever that means, right? Like mediums always fit me, so yeah. All right. Thanks. I guess I just have to, I'm gonna have to like cancel everything for the rest of the day though, so I can get home. I kind of want to start like just designing something like that. Compact necessarily. Don't forget, the simplest closed sets are just singletons. Just a single point. Singletons are closed and compact. And we could send one of these to Abbott if he's even still alive. Just like, no idea. Use compact set, right? Can I subtract something from this that's closed that ruins its beautiful compactness? Yes? Like what, Kayla?
I
Bit.
mean, indeed.
Yes.
Well, you could subtract its endpoints. That would be
Beautiful,
terrible.
thank you. Yes, exactly, yes. So we could literally just subtract, so if we let K equal closed interval A to B, and we let F be just the single point A, yeah, nice. So K minus F is the half open, half closed interval, and that we know is not compact, because it ain't closed and bounded. That seems like a good enough stuffs for one day. Yeah, yeah. Okay, we did some math, we laughed. That's a good fucking day. That's the best real analysis day ever. Okay. Hey, thanks everyone. So homework. Does anybody need a new homework set yet? That's cool. Yeah, that's fair. Yeah. Let's keep it. Let's keep things simple. Oh, and in terms of the remember I was going to have a vote. Do you want the exams to be your top homework? How about this? I'll just do what works out best for you.
Okay.
Does that sound good? I kind of feel like the thing that's going to work out best is if you take the best homework scores and amplify them,
Yeah, that's fine.
right? Or not? Yeah. I don't know how that could hurt. And there's a math problem for us. We could, yeah. Yes, sir. Thank you, Kayla.